All right, let me try another video solution here. How about number 54 here from chapter 28? It says here, a young man owns a canister vacuum cleaner marked at 535 watts at 120 volts in a Volkswagen Beetle, which he wishes to clean. So he parks the car in his apartment parking lot and uses an inexpensive extension cord that is 15 meters long to plug in the vacuum canister. You may assume that the cleaner has a constant resistance. If the resistance of each of the two conductors in the extension cord is 0.9 ohms, what is the actual value of power delivered to the canister? So this is kind of that terminal voltage idea again. So we have a power supply, and for lack of a better picture, I'll just do kind of a battery. It's probably actually plugged in, and call it 120 volts. And what it's saying here is if you didn't have any losses and you plugged it in, and basically this is implying that you're going to have losses because of the long extension cord, but there would be some load resistance, and when you plugged it in then, the power, which we can write as IV or I squared R, or in this case probably best to write it as V squared over R. This is what can tell us the resistance of the vacuum cleaner is, because we know that it's designed at 535 watts for the power, and at 120 volts it'll have a certain amount of resistance. So this is kind of the first step to find out, okay, what's the resistance of this vacuum cleaner? So I'll take the 120 and square it and then divide it by the 535 and say, okay, we're looking at a resistance of about 26.92 ohms. All right. So I'll keep that in mind, because they do say that go ahead and just assume that the vacuum cleaner has a constant resistance, probably a bit more complicated in reality than that. But that's a good start for our elementary electronics here. And then we can say, now what we're going to actually do, though, because we want to clean the car, and the car is, got to stay in the parking lot. The apartment's kind of far away. So we're going to run this long extension cord, and by cheap, they probably mean that the wires are kind of thin, so you didn't have to put too much money into the copper wires. And so we've got this long extension cord, which they label as 15 meters, so there'd be wire for the current to go down and come back. And then we're going to plug in the vacuum cleaner. So there is the 26.92 ohms there. So each of these have a resistance of 0.9. And so the question really is, what is the power now being delivered to the vacuum? Because it won't be as simple as before, where you only have the load resistor. Now we have the wires getting warm and using some of the power here. And so maybe we can just notice that these would be in series here. And so if I go to do the currents, I could say, okay, we're still plugged into 120 volts, and we're going to divide it by the resistance, which is the 26.92 from the vacuum cleaner, but they're in series with a 2.9s due to the fact that we've got this long wire. So I'm going to add 2 times 0.9 to this. Oops, and I multiplied. So let me take that again and add 2 times 0.9. All right, so that's about a 28.7. So if I go 120 volts and divide it by that last answer, we're looking at about 4.1, I'll just go 79 amps. So there is the currents running through with this extra resistance here. So again, to find out the power to the vacuum cleaner, maybe I'll go I squared R. So there's the I, and I'll square it. And the R is the 26.92. And we are looking at about 470 watts. So it's probably a pretty poor way of running this vacuum cleaner, because it could be running with a lot more power and probably working a lot better. But because we ran with this long extension cord, we have a drop in voltage, or put another way, the terminal voltage is less. So you're really not running the vacuum cleaner on 120 volts. There's a drop down because of these two extra wires. And so there's a drop in the amount of current, which is a drop in the amount of power here. So there's the first part here of the resistance of each of the conductors. What is the actual power? Then B says if instead the power is to be at least 525. So if you argued that it wouldn't work right, or maybe not even enough to even turn over the motor, you got to get at least 525 watts for it to even turn on. I've actually experienced this with my air compressor, that if I run an extension cord here and try to turn it on, it just is below, and it just won't work if the extension cord is either too long or too cheap and too thin, or actually any extension cord. It actually says on the plug, do not use with an extension cord, and the idea is to plug it in close to the wall, like back here, and then if you wanted to use it far away, get a long air hose. So that's the idea of the air compressor. And so in this case, maybe, they'd be so far the vacuum cleaner doesn't even work. So this question, I guess, is, kind of hypothetical, that saying, okay, we really would need 525 watts for this to work. So again, if we kind of do this in reverse and say, okay, this is I squared R. Oh, let me get to the question. If instead the power to run it needs to be at least 525 watts, what must be the diameter of each of these two? Ooh, now that's a little harder than I thought they were going to ask. But okay, let me start here, because we know then that the resistance still is the 26.92. So this would be the minimum amount of current needed to operate this thing. And so 525 divided by 26.92, and taking the square root of that means that they're trying to say if you don't have 4.416 amps, it's just not going to work. And as you can see back in part A, we had under that, which is why we had under the power that this is saying here. So we need to have at least this much current, apparently, is what there is saying here. It says, instead the power needs to be at least 525 watts. So we need at least this much current. So coming back to this particular diagram here, and again, taking this extension cord still to be 15 meters long, they are going to have some resistance, let me call it R, and then the vacuum cleaner at 26.92 ohms. Okay, and as we plug it in, getting current as voltage divided by total or equivalent resistance, this current we need to be 4.416. So we needed at least that when we plug it in. And the resistance is the 26.92 plus 2R. So again, we can't have the resistance too much, otherwise the current will drop below this minimum. And as we already know, a resistance of 0.9 would be too much. As we can see, we just don't get enough power. So this would tell me then what resistance I need to have, and a small amount, or at least smaller than 0.9 is what this should come out to be. So I'll just rewrite this as 2692 plus 2R equals, and so I'm going to take the 120 and divide it by that last answer. And so that's 27.173. And if I then subtract off the 26.92 and then divide that by 2, this is saying that our extension cord really needs a resistance per wire of this much or lower, 0.1265. It needs to be at least that low. Anything higher than that is going to create a smaller current than this, which reduces the power below 525. So the question again says, what must be the diameter of the two identical, and there it is, copper conductors? Okay, so dropping back a chapter, we know that the resistance then is the resistivity times the length times the area. All right, so if we're making this out of copper, then with a resistance of 0.1265, I can look up the resistivity here of copper. Let me grab the textbook here and flip over to chapter 20. Oh, I bet that's 27. I know there's problems from 28, but it's here in 27 that they give here it is, table 2, they give the resistivity. Now, of course, remember, this is also at 20 degrees, and they don't say anything about the temperature. So I'm going to go ahead and assume they're talking about 20 degrees. But we are outside. This is an extension cord outside, and we're using the cord. So I have a feeling the cord probably even goes up a little bit. But ignoring that, since we really don't have anything to work with on it, let me jump over here to the copper and just double check. Let's say two identical copper. And it's 1.7 times 10 to the minus 8. Okay, so 1.7 times 10 to the minus 8 is the resistivity. And they did say it was 15 meters long. And then, of course, the area, kind of assuming they're round wires, would be pi r squared. Let me do a little r there. And then I should be able to calculate what's the radius and then, of course, the diameter. So let's see here. If I take the 1.7 times 10 to the negative 8 and multiply it by 15 and then divide it by 0.1265, then divide that by pi, and then take the square root. This would be the 8.01 times 10 to the minus 4, or diameter, 2 radii, equaling diameter, times 2 would be 0.00160 meters, or if you like, 1.6 millimeters. So I need to have, a wire that has at least that diameter. Anything smaller than that is going to be too much resistance to cut down on the current, which cuts down on the power. And so that's kind of the idea here. Now C says repeat part B, but assume the power is to be, 532. No, okay, so I'll just go through and do it again. And then they have a suggestion. You should do this problem in symbolic so you can just change your numbers. Yeah, that would have been helpful. Should have done that a little earlier. However, I'll just repeat it with a small change in my calculation. It will begin back here, and instead of this 525, I'm going to put 532, which then makes a current of, and so I'll just grab my calculator here and say, okay, here is 532 divided by 26.92. That'd be current squared, and then take the square root. So 4.445 amps in blue here for part C is what I would need for the currents. So then coming over to here, this number then becomes 4.445. And going through the same logic, I can get a new R value in blue, which of course should be even lower than that. But I'll take that number. Actually, I'll mentally move that. So this would be 120 divided by this last answer when I move that over. Subtract off the 26.92 and divide by 2. So here we need the resistance to drop down to 0.368. And just as a rough number, that's, well, 12, and that's not a 4, 3. Anyways, if that was a 3 and that was a 12, this ratio would be a factor of 4-ish. Might be a little less than that. But if we want it to drop by a 4, we would then roughly have to take the radius and double it because it's 2 squared. So we're probably looking around somewhere, whoops, I meant to put millimeters here, by the way. Millimeters. So my guess is somewhere around 3 millimeters, which is a pretty thick wire. So that would be a little much to ask. But that's a guess. So let me just keep going here. So this is the resistance, which I will put there. And so let me kind of do the same thing. Let me go the 1.7 times 10 to the negative 8 times a length of 15 meters. And let me divide it by that resistance. So that's the last answer. And then, of course, we also have a pi underneath. So that's going to be r squared. And so if I take the square root, we're looking at an R of, so in blue, R is 0.00148. And so now if I double it, we're looking at 0.00297 meters, or 2.97 millimeters. So about 3 millimeters. Yeah, so my guess was pretty close. Of course, it wasn't a real guess. It wasn't until I got here that I bothered to even try to guess what it is going to be. But that's the idea. Hope that helps.